Let me introduce you, João. Thank you for giving this presentation. Really excited to hear about how AI can be used for resource definition and understanding the deep sea environment. So, João, over to you.
Okay, so thank you, Oliver, for having me. It's a great opportunity to present this. So, without any further delay, I'll start to present. So, give me just a second here. Yeah. So, yeah, great. So what I will do is I will just first talk a little bit about DeepFocus, and then go through briefly to the critical minerals demand, and also some of the challenges in exploration, deep sea mineral exploration, and then how we use AI and how we do it, this process, and show you some examples. Okay. If you have any questions, please go forward and do those questions. So basically, DeepFocus is a Portuguese startup created in mid-2023 and focus on basically providing intelligence for responsible deep sea mineral exploration by use of AI-based data processing and analysis. Our services basically include geological consulting, new target generation, review and analysis of existing exploration assets, and also performing some habitat mapping. So in terms of critical minerals event, this is highly discussed, so nothing new for you. As you know, the green transition and the advances in digital technology are driving the demand for critical minerals, and minerals such as cobalt, nickel, copper, lithium, and rare earths, which are often referred to as critical, are associated with electrification, renewables, and energy storage. But their significance extends well beyond the energy, from AI and robotics to high-performance materials and aerospace. These minerals' contribution to industrial and technological developments is increasing, with a broad economic and geopolitical implication. And as you can see from this map, the global distribution of the production of these minerals has many others. It's basically concentrated and controlled by a few countries that often don't have the good regulatory framework that offers protection, environmental protection, and also protection for the human rights, and also prevents accountability. So, coupled with the lower exploration budgets over the last decades, this means that today there is a huge dependency on imports of these minerals by most of the countries, in particular the Western developed countries, which in turn mean that the production of raw materials needs to increase. So, as a result, the search for new sources of these materials has taken the interest of many governments, private companies, and also investors, from dry land to the deep ocean. This is not really a surprise, given that the oceans cover about 70% of the Earth's surface, and is a dynamic and biological rich environmental, featuring basal plains, mid-ocean ridges, ocean trenches, seafloor volcanoes, and various types of mineral deposits rich in minerals like nickel, cobalt, copper, and also rare earths, that again constitute an alternative source of minerals relative to mining on land, as well as contribute to the supply chain diversification and higher mineral resource sovereignty. The interest in deep sea minerals deposits such as nodules, crusts, and massive sulfides is basically due to their polymetallic nature and high grades. For instance, it's estimated that polymetallic nodules deposits in the Clarion-Clipperton zone in the Pacific Ocean contains resources of these base metals estimated between 1.2 and 3 times greater than the entire global resources on lands. I'm talking about manganese, nickel, cobalt, and yttrium, for instance. And also cobalt-rich ferromanganese on the seamounts of the Northwest Pacific Ocean are estimated to contain enough cobalt to meet, for instance, Japan's demand for over 80 years, and with enough nickel also for 12 years. And lastly, seafloor massive sulfides in the Norwegian Sea and also in the Greenland Sea that are estimated to contain about 38 million tons of copper, about 3.1 million tons of cobalt, and about 1 million tons of serum rare earth, often used for glass. Okay. So, but the deep sea also one of the least explored parts of our planet and home of a vast and highly diverse ecosystems and sea creatures, some of them possibly unique, that rely on food coming from the surface and in a process known as marine snow, and also plays a critical role in the global climate regulation through nutrient cycling. So this means that we have the duty to do things right, but right from the beginning. So we must ask ourselves, how can we do better? And this is not only by developing technology to source these resources, although it's still a major improvement, but rather it's about trying to innovate and apply and combine new approaches, less impactful, right from the early phase of the mining value chain, to make sure that if this activity goes ahead, it's performed only in selected areas with high mineral resource value and with the minimum impact on the marine life. So this means that we have to work better on the prospection and exploration phase. If you want responsible sea mining to happen, any area or project selection for investment or detailed mapping or sampling should be made carefully. So if this first decision is done wrong, the probability of fulfilling the investment goal is highly diminished, and the potential for spending too much time and money on unpredictable exploration or in highly sensitive seabed areas is much higher. And for that, we believe that AI can greatly enhance the discovery of these sites where you can find high-value mineral deposits in the seafloor, and also help to make seafloor mining activities more friendly to the environment. So, but exploration for mineral deposits is not easy. It takes a lot of data and expertise to define high-value target area to explore, and several studies on land mineral deposits indicate that success ratio of exploration is less than 1%. This means that for every 100 prospects, only one will be a mine. And this success ratio is worse for what is called the greenfield exploration. That is, while the brownfield project can range from advanced development stage with a known resource to proven producers, always in the surrounding of existing mining operation, the greenfield projects are characterized by minimal to basically no data or exploration carried out. The information is typically limited in terms of structural setting, the local geology, and in cases also limited in terms of geophysical or geochemical or even sampling data. So this means that the exploration team must rely on geological models and experience to locate potential deposits. And this has a consequence. The creation of value, that is getting the right area or project, demands for that the ongoing rigorous analysis, testing, and prioritization of all the opportunities that you can map out in an area that you are interested in. Also, just to keep in mind, the estimated lead time for discovery to production can take over 15 years, and roughly about 70% of that time is spent only in exploration and resource evaluation studies. And this represents a serious challenge. This process can be a little bit harder for deep sea mineral deposits exploration due to the harsh environment itself, but also the need to ensure the protection of the ecosystems. First, because deep sea exploration costs are high. Second, it is a time-consuming and risky process, often limited by the lack of data, expertise, and the tight budgets. It usually requires about 3 to 5 cruises to start defining the mineral resources and develop an environmental baseline and characterize, for instance, the oceanic layers. It is also a process that also requires vast areas to explore and a lot of information to process, integrate, analyze, and to make a discovery. So again, that is why that the selection of the area is key. And even with today's technology, the multiple service technology, there is always the risk of spending a huge amount of time and money only to conclude that an area is not viable, or even worse, overlooking a potential bonanza. So despite all the data available out there since the 70s, there are still challenges to define high-value target areas, or to have actionable insights to explore key areas in detail and support the decision-making process, even in known regions. So this is difficult. And you can see this on even in places that are studied, okay? And this is just an example for the data available in the Clarion-Clipperton zone, both in terms of the nodule occurrence and also the data containing also information on the macrofauna. And as you can see it, there seems to be a high density of data, but when we zoom in, there is a very lack of data. The data is not clustered, and this brings challenges. The same is also for the marine life data, where you can see it that is basically concentrated on areas where there is exploration. So this could be a quite challenging process because of when you select an area of interest, the data that exists could be quite limited or sparse, okay? So this creates huge challenges both for private and public stakeholders. On one side, private companies want to attract investment, de-risk their projects, and perform in an environmentally responsible and cost-effective way, whereas regulators that govern mineral exploration and mining want to develop policies and strategies to mitigate and also map environmental impacts and also the resource use, and ultimately also to communicate opportunities so that the private companies could invest. And for that, we believe again that AI can greatly enhance the exploration success, also contribute to more environmentally friendly seafloor mining activity, okay? So we have developed several tools to help support the exploration decision process and enhance our understanding of an area in terms of environment for faster, smarter, and also safer mineral seafloor exploration. These tools are basically proprietary machine learning workflows that we developed and that allow to inform on target generation, resource estimation, as well as on species distribution, richness, and associated parameters, both physical and also chemical, geochemical parameters of the water column that interact and determine the distribution and richness of the ecosystem. So in terms of products, this is basically what we offer for the side of the mineral resource and also the marine environment. And in terms of other features, that the other product that come coupled with what we do, we have examples here from bottom current velocity and also direction, also some information on the bottom oxygen dissolved. This could be also performed on selected depth levels. We can also provide some information on nutrients, phosphates, silicon, other type of nutrients, and also provide some information on the geological and structural features of an area of interest. But how we do this? So basically, we gather all the data that we can find coming from either satellite, AOVs, or even sampling to create a database, which is then processed, divided, and run to a series of machine learning models in order to find the models with the lowest error and provide a predictive map, okay? And basically, this approach allows us to assess areas of interest across scales that could be on a regional size, regional scale, like, for instance, the Clarion-Clipperton zone, or to an area, exploration area with a local, more local scale, okay? Now, in a bit more detail, and also depending on the objective, all the data collected is to provide information or derive some specific features. This is based on either the mineral systems or a system that we want to define for mapping particular species or an ecosystem, okay? And this is then performed by several processing steps, which then result in a database. So after that database, different data sets with different train and test splits are then created from that main database to see which data set better represents the problem and which model is more accurate and also consistent, okay? And well, according then also to the task itself, the objective, basically the evaluation of the models is performed by the use and combination of several techniques, as, for example, listed in this table. So now for just some examples. Here you can see an example of the approach that we have performed for the CCZ, where we have assessed the nodule abundance and also quality for several areas with about 300,000 square kilometers. And basically the results achieved show that the model error is about 5 kilograms per square meter, and the models tend to show, at least the selected model for this objective, shows an accuracy above 70%. We also assess the CCZ in terms of what might be the remaining resource available, given all the studies and activity in the area. and excluding all the contracted areas and also protected areas. And our assessment indicates that there is still room for discovery of high-value target areas in the Clarion-Clipperton zone. In this 1.8 million square kilometers area, you can find at least 33% of areas that show high nodule abundance, well above 8 kilograms per square meter, and several high-value target areas that you can be defined there with with the nickel plus copper grades above 2.2%. Okay. Okay. And just for the last example, we run also our analysis in an area of interest located in the northern equatorial middle Atlantic ridge, this time for SMSs. This area is located basically between 7 degrees and 16 degrees north. It's an area that extends for almost 900 kilometers and long and about 200 kilometers wide in places, and accounts for almost 250,000 square kilometers. So just to sum up, the results show that basically only 50% of this area is permissive so for seafloor massive sulfides to occur. Okay, that is the area that is favorable for this type of resource to occur, and that also the exploration should focus mainly between longitude 14 and 15. And within that area, you basically can find 4 new target areas for detailed mapping and sampling. So this allows you to guide and make decision in terms of a more detailed exploration work. And you can see also that these areas seem to show continuous copper grades ranging between 4 and 12%. And that's it. Thank you. I hope that I was not too fast enough or talked a little bit faster.
This was wonderful. Thank you for that. What I would like is, if people have questions, please use the hand icon, the raise hand, which is in the bottom of the screen, towards the middle, just left of the red hang up button. And then in order that people raise their hand, we will allow you to basically, we'd ask you to unmute and ask your question. Yeah. So Trevor, you are first. Please unmute and ask your question.
Thank you, Oliver. Hope you're doing well. João, for the studies that you've done off the coast of Japan, do you have any details around the concentrations of minerals in those particular deposits?
I didn't understand the question. For the study that we did around Japan, right?
That's right. Yeah. Just would you elaborate on any details of the findings of that particular study?
Well, you are talking about, if I'm not will not mispronounce the island name, is Maritorishima, right? That study on nodules, right?
Yes, sir.
So what we did is just to try to assess all that area, that ZZ area, based on the study, or at least the news that came up last year or 2 years ago. Mm-hmm. And what basically we find out is that at least we have different models for that, but at least one of the most interesting models show that in addition to the areas where all the studies and all the exploration was focused, there was an area further north that seemed to have higher nodule concentration. They also show a bigger a bigger continuous area with high nodule abundance. I think I want to stop sharing, but to see you guys, but I don't know where. My apologies for that. This is the second time that I use Google Meet.
No, that's okay. Yeah, so that's exciting news that there's, you know, additional deposits outside of the ones that have already been popularly talked about. So there's room for expansion there. So that answered my question. Thank you.
Okay.
So I'll ask a question, as we don't seem to have any others quite yet. So the question is, talk a little bit about your business model. How do you commercialize your technology?
So basically, what we do now, we provide consultancy, and depending on the objective, we could try to support either the resource definition and also first the selection of an area of interest, and within that areas to provide or to do more detailed studies, and then also to characterize the area in terms of environment. Okay, and we do this consultancy. In the long term, we could do first assessment of that, and then later, if the work is to continue, we can integrate the data that is collected to try to enhance all the modeling of the area, so that we can then gain further knowledge and also focus more or detail more the areas of study. We started this in the late 2016, when we developed the first MVP of this tool. The first idea was to use this as the software has a service, but then we changed this to do more in the basis of consultancy. Okay.
Great, thank you. Victor, please ask your question.
Yes, thank you very much, and thanks for letting me participate. I just have a general question more about the overall business model, and this is probably more directed towards you, Oliver, than to João, because I don't really have any issues with the AI predictive models for looking at concentrations or mining capability on the seafloor. But really it comes down to one of relevance. If you look at the, your own concept economic model version 6, if you're collecting nodules, which is the primary business of Impossible Metals, you'll be producing about, 5 kilotons per year at your full production rate of 6.7 million tons per year, and about 68 kilotons of nickel. And if you look at terrestrial world production, those numbers are dramatically higher. About 312 kilotons of cobalt a year, 4,300 kilotons of nickel per year, where even at your full production rate, your contribution of Impossible Metals to world cobalt production will be less than 2%. It'll be 1.6% for nickel. And while I admire what you are trying to do to make a more environmentally sensitive technology to deliver the few metals out of the 50 that are designated critical, we're really only talking about nickel, copper, and cobalt as being accessible from polymetallic nodules. I mean, how can people have confidence in the overall business model that this is not something that's going to transform the mining world, that it's actually less than a 2% solution to the overall terrestrial mining issue?
So that would be per a mine location. There are 40 exploration license areas, so you have to times those numbers by 40, and then there's plenty more to be discovered. So we believe we can build the world's biggest mining company with deep sea minerals by having many concessions and partnering. So the scale of the business that we can build is bigger than BHP.
I see. Well, but also let's talk about the other issue, which is when you're talking about polymetallic nodules, there are really only 4 metals that are involved in recovery, and that's copper, nickel, manganese, not lithium, not rare earths, not in any meaningful economic amount for polymetallic nodules. And yet there's so much discussion with respect to deep sea mining that it's going to solve all these critical metal issues when you're really only talking about the two most valuable ones, which are cobalt and nickel. And so do you think it's a bit of a stretch to make the presentation so much about solving critical minerals issues when really deep sea mining is really only involving cobalt and nickel, because there's so much copper terrestrially available, as well as, manganese is the lowest value element of the four?
So I don't think you understand the basics of mining, Victor, with respect, because it's not about how much is available, the resource. It's about a reserve. What is economic to extract? That's what matters. And the reality is that copper is becoming increasingly more expensive to extract from the ground. The average grade now is below 0.5%. We have 1%. And so when you talk about reserves, which is what is economic to extract from the ocean, it will have a significant impact on the industry because the grades are so much higher. And, of course, there are 50 or so different critical metals, but nickel, copper, cobalt, and manganese are very, very important. It's not to diminish that lithium and other rare earths are not important, but the total addressable market this year for just nickel, cobalt, copper, and manganese is $500 billion spent this year, and it's forecast to double by 2035 to $1 trillion a year. I think we can build the world's biggest mining company by having a large percentage of that over time.
Yeah, well, I very much appreciate the answer, and I certainly admire the passion that you have. I just simply think from an economic standpoint that there's a massive assumption there on the economics of the technology that you would use to try and capture these four metals. But even just to talk about copper, even at your full production rate predicted in your model version 6, that's about 65 kilotons per year against a world production of 29,000 kilotons. It'd be less than 0.23% of world production. You would have to massively scale in order to overcome the huge advantages of terrestrial mining. And I just simply don't think that the cost structure that you will have will be competitive with what terrestrial mines will do. Even with the decline in the metal grade, they will also make technological improvements just as you are doing. But that's it's a difference of opinion.
Yeah, with respect, Victor, I disagree, but I think we should move on to allow.
Okay, fair enough.
If you want to have a debate on a webinar coming up where we can spend an hour, I'm well up for that.
And I appreciate that. I respect that a great deal because I admire the discourse among the people that are involved in the debate. So thank you again. I'll yield the floor, of course.
Just a quick comment, if you allow me, Oliver. So the point that you make, Oliver, it's quite important because people often in mining don't realize what is the difference between an occurrence and a deposit, and then the resource and the reserve. So it's really important for people to understand that what makes a mine or a deposit is when you define the reserves. Okay, you know that it's economical viable to extract that resource from anywhere. Okay, and the second point is that copper comes from a lot of types of mineral deposits. The main ones are called porphyry copper deposits, basically the mines in Chile and also Peru. And the grades are really, really low in that type of deposits. The upside is that they have a huge, they are large. And because of that, they are economical, feasible, and they have also other type of metal like molybdenum associated, plus others that make that type of mining really, really appellative. Okay, just that comment. Okay.
Thank you. So let's go to Kirsten, please.
Hello, thank you very much for this really interesting presentation. I have a very simple question, so relax, it's nothing as complex as the last one. And also, I hope not controversial. When you showed us a map of an analysis of how much in the Clarion-Clipperton zone, how, you know, a model of which areas still contain significant amounts of polymetallic nodules. In that map, I couldn't quite see. I think your estimate was something like 33%. Was it right? It was more than 8 kilograms per
square meter. So that map was basically an analysis that we performed, thinking out all the areas that are now contracted and also the protected areas. So
you answered my question.
Sorry?
That was it. You answered my question. Thank you very much. That was exactly my question, whether the APIs were included or excluded in your
excluded.
Thank you very much.
Okay. I just was going to refer that in some, actually in some protected areas, you can find interesting abundances and also grades. Okay, just that point. At least,
so they should. I mean, if they're representative of all the habitats and, you know, in the Clarion-Clipperton zone, then, you know, they should have the same nodule densities as some of the licensed areas.
Yeah, people in the ISA are doing a good job. Yeah.
Thank you very much.
Thank you.
Kieran, please.
Can you hear me? Okay.
Yes.
Yes.
Okay. Thank you, Joe, for the informative presentation. On your slide number 16, there was a mention of ecosystem AI. And
Yes.
I was wondering whether you could, you know, share some more information about that component of ecosystem AI. And to increase its effectiveness, would you recommend pre-harvesting survey of all the faunas using the deep sea AUV? You know?
I didn't. Sorry, I didn't understand just the last part. Serving all.
Okay. So if you want to increase the effectiveness of your ecosystem AI module, what would you recommend? And in that recommendation, would you include a use of pre-harvesting survey of the site using an entirely different AUV? So therefore, with the reinforcement learning, your module will be much more effective, you know.
Yes,
Right?
yes.
Does it make sense, you know?
It makes sense. So basically, this type of approach lives with data, and if you have a lot of data, that is good. But then again, that could be also problematic. But basically, how this module basically works. So depending on the objective, we have basically all the pipeline that we try to build in a modular way, so that then we could adapt easily to the objective of a given project. But basically, we collect all the data on, for instance, a species or group of species that could be representative of ecosystem that is, for instance, associated to polymetallic nodules or for instance, seafloor massive sulfides, and then try to model that by either integrating where they occur in terms of position, geographic position, and also all the features, both geological, if you want, and also oceanic features or parameters that could influence their occurrence. So we integrate all that to try to model and then predict the occurrence or the spatial distribution of that group of species or a particular type of species. Plus, also, if we have the data, how much could exist, if it's too high or too low. So if you add more data that could help that could help characterize that species occurrence, that is a good thing. But as I said, sometimes too much data could bring some noise, and then the model learns background noise, and that is not so good. That's why we try to test and use different types of machine learning models, and then from the 3 best or the 5 best, try to look for to them and try to optimize them so that we can provide the result or the model, the prediction with the model that produces the lowest error possible. Okay, with the available data.
Thank you. Yeah.
Okay.
Okay, Dubona, I don't know if I got the pronunciation correct. Please ask.
Thank you so much, Mr. Gunasekara. I hope I'm audible.
Yes, you are.
Okay, Mr. Carvalho, thank you so much for your presentation. It has been very informative. So my question also actually relates to ecosystem AI, if I may. So I think the first question I had has already been answered, because I was asking about whether how much have you tested it, and what is kind of sort of the accuracy level you would say. What is the level of I don't know, hallucinations as you call them, and I guess my real question is, if there is enough data and if this system works well, the ecosystem AI, I mean, how much could it really feed into, say, for example, you know, the determination of baselines? I mean, that would be one question. The second would be, given the fact that we really have not studied deep ocean marine environments as much as we probably should have. I mean, as far as I know, 70% of it is not studied as yet. So how do you, I mean, what is the data that you are relying on, and how do you know that it is going to be effective when you do not have the data for species that have not been studied, is the second question that I have. Thank you so much.
Okay, so what I can say is that the models will always, all machine learning models will work better for the type of data, or if you want more specifically, for the areas where the data that data was collected and the model was also based on. Okay, this works for all things involving machine learning. So the second thing is that because we try to integrate all data and also parameters that you can either use directly or derive from that data into model, test them by combining them into different data sets to try to see how well they correlate with a given species or species, you know, to define an ecosystem or an habitat. We can have like a broader input or framework that contributes for the model to integrate different aspects, different parameters that influence the distribution and also the richness of that particular species or group of species, okay, for a given area. We also, as I said, integrate oceanic and also parameters, both physical and also biochemical, that, as you know better than for sure than me, because I'm a geologist by background, so those factors or those features, together with the seafloor morphology, the geology itself, the type of sediments, also influence the distribution and also the occurrence of the marine organisms, you know. So we try to integrate all that and put in to run, test those into this workflow to, as I said, to try to give or get the best result possible given the data that we collected. So, and basically we are collecting data that is available on, for instance, on ISA deep database, that is data that is reviewed and also is being reviewed, but you have a kind of you have for sure scientific people or scientists that are marine biologists that are that have worked and that are also working on that data, so that it's an insurance that the data has some quality. Okay, and then what also differs is that the type of approach that one can make with the data, okay, and what type of features you really take into account so that the model gives the best results possible, again taking into account the available data. So it is true that we don't know yet enough about the deep sea, but we know something, and we have already areas that are fairly well sampled in places. Of course, when you zoom out, those that areas could not be so well sampled, but you can take those areas as a reference, as a baseline, and then try to compare with areas where you have no data or a few data, and try to see if you find similarities, so that you can then try to characterize that area and have a baseline for that area. Did I answer your question?
Yes, you did. Thank you so much. Thank you.
Don't see any other questions. Anybody else? Kirsten, please.
Sorry, me again. Just out of it, now that you talked so much about the biological data, and I am a marine deep sea ecologist, and I know how inherent tricky the data is. I mean, you have all kind of issues with, you know, statistics and what have you not. Do you have any ecological experience on the team helping you to? Yeah, good. Yeah, good to know. Yeah, thank you. That was all we. Yeah.
Okay.
There's a question in the chat. I don't know if you want to look at that.
I think with over 30 years of exploration contracts already granted by the ISA, yet binding exploitation regulation and UNCLOS still unresolved. How can companies leveraging AI-driven deep sea mineral target ensure that their activity remain legally secure and aligned with the control with the common heritage of mankind principle, while avoiding future disputes over liability and compliance? Well,
so let me have a go first, and then you can add. So the ISA over 20 years ago adopted the exploration mining code. So that is legally adopted and in force, and that's why there are over 31 exploration licenses that have been awarded. So all of the research that's being done to define the environmental baseline and the environment is being conducted under exploration licenses, which were, the mining code was adopted, I believe, in 2020, in the year 2000. And there are approximately 31 of them already awarded. So all of that is completely legal and within the ISA framework. What has not yet been adopted is the exploitation, the actual commercial mining code. But there is something called the 2-year rule that has been triggered, which allows any contractor that has collected the correct amount of environmental data and is ready to go to now submit an application. And so our hope is that the ISA finishes the exploitation mining code. It has been working on it for 14 years. It's not yet finished. They have a consolidated text. They've done a couple of readings. There are still a number of areas that are not yet have agreement, but our hope is that this will get finished within the next couple of years. If it does not, then of course there is the 2-year rule that allows for exactly this scenario. which would allow contractors to move forward. And of course, there is what the metals company is doing, which is completely bypassing the ISA. So hopefully that answers the legal side of exploration.
Yeah, yes, and from at least from the side of the AI, so also the contractors must periodically present reports from the activities to the ISA, so annual reports, also a plan before that. And what this can help is because some of the those players don't have the chance to do cruises campaigns for year after year. So this type of approach can help them to do that reporting by, for instance, trying to analyze all the areas that they could be interested in. If they have scattered areas, also provide in terms both of the resource and also in terms of the environment, help them characterize the areas so that then they can then start to focus their and relinquish the areas that they have contracted and focus only on the areas that are more interesting. Okay, this can help speed up things, and also if the regulator wants to use some of the information, they can put it publicly. So I think also this helps or contributes to more transparent approach and also development of work, because it's a third party, not one that is tightly linked to the company that is performing the exploration, doing that assessment. So that's my point.
Yeah. So unless there's any final questions, I think we should wrap. And I want to thank you, Jose, for the presentation. I think it was super interesting. We will be pasting this on our YouTube channel and on our podcast platform next week. And look forward, we've got some exciting webinars planned in October. So thank you, everybody. Appreciate your time.
Thank you.
Thank you.
Bye-bye.